potential. If it's a semi-metal instead, there is a distribution of values. As you can see, there is a distribution of values, very much so. So even when, for example, it's negatively charged, some of the atoms have a very positive electrostatic potential, and the same one is positively charged. So the potential is not constant across the electrode, and the graphene cannot be assumed to be a metal. Then there was a question is if this polarization effect has any effect on the water orientation, so the orientation of the water at the interface, and we thought this was going to have an effect on the surface tension. So what we did, we look at just the orientation of the water molecule within the layers nearby the surface of the graphene. And again, we look at pure water and 2 different concentrations of sodium chloride. What we found is that there is indeed an orientation, as you expect. This orientation, however, happens only within the first 1 nanometer, so very, very close to the surface, and then disappears immediately as soon as you move away, basically, from the first one peak, 1 or 2, peak of the density profile. And when the graphene is uncharged, this orientation is not really affected by the polarization effect. So then we were interested in look at the surface tension. Then we wanted to see how is the surface tension of this water graphene interface, and also the electrolyte. But here I'm going to just show you the results we have obtained so far with water and graphite. So this value of surface tension is very interesting in general, because there is this definition that graphene is actually transparent, meaning that whatever you, so basically graphene might be able to change electronic properties of a substrate, but is not going to change its wettability. That's why they say is transparent. However, if you look at in the literature, the experimental value for the surface tension varies quite a lot, depending on where has been measured and who measured it, the procedure, etc. And so most of the data are actually for the contact angle, and you can see they are very different. So we were interested in see from molecular simulations. So that means that you avoid any problem of contamination, for example, which is known as a problem in these experiments. How much is the surface tension and how the surface tension is affected by the substrate. So the way we calculated the surface tension is we use the mechanical definition. I guess I'm very close to the end of the talk. So, but basically what we did was we calculated, so the mechanical definition through the stress tensor, that can be divided in the kinetic part and the potential part. This has been nicely explained also today. So the surface tension can be calculated as the integral of the difference between the pressure normal to the surface minus pressure tangential to the surface, and these are related to the value of the stress tensor. So this is the procedure that you normally use to calculate surface tension between liquid interface and liquid gas. But you can use it also to calculate surface tension between liquid and solid. So what we did, we performed 2 simulations, one in which the graphene is surrounded by water on both sides, and one where there is basically insulator on this side, which is vacuum for us, and water on the other. So what you can do, we use GROMACS. There is a special tool of GROMACS that is able to basically calculate the stress as a function of the distance from the graphene. You slab the box and you calculate the stress in each of the slab. And then what you end up with the distribution looks a little bit like that. And then you integrate the curve and you obtain the surface tension. And at the end, for example, in this case, you have the surface tension between the solid and the liquid, and also the liquid and the vapor that can be used to verify your procedure. And then you have both, basically. So we look at these 2 setup, and also what's the effect of having more than 1 layers of graphene. So these are the results, really. So we calculate the solid liquid surface tension for number of layers, increasing number of layers. For this system where the graphene is fully wetted, and this system where there is vacuum on this side. So what we notice, okay, first this number matches nicely with the fairly recent experiments from Susan Perkins in Oxford. So we were quite pleased with the comparison, so we thought we were doing things right. And what was interesting was that there was a quite big difference in calculated surface tension, where basically the graphene is wetted, fully wetted, so it's like in a dispersion, and where instead is supported. And the surface tension was also decreasing as you were increasing the number of graphene layers, and this was also in agreement with previous calculations when they were looking at surface tension. So then we tried to clarify as why there was this difference between fully wetted and partially wetted graphene, and we look at the topology of hydrogen bonding. We use this ring statistics procedure that is able to basically tells you how many water molecules are within one ring formed by only hydrogen bonds. So this is the distribution. Basically what we found was that, so if you look at this ring statistics in bulk water, what you expect, right? You have a peak here. So usually between 6 and 7 water molecules are all linked by a hydrogen bonding structure. When you have an interface, these numbers slightly shift to a lower value. But if the system is fully hydrated, you see that the numbers really are very similar in respective to the number of layers we have. It's a bit more confusing here, where the numbers still shift to a lower number, but you know, if you have one layer, then the values are quite different, and then they shift back closer to the peak in the bulk. When you start to have 2, 3 layers is the same as 2, and then 6 layers. So basically what we thought that is, so what if this shows, we haven't done a lot of analysis, but basically the point is that the presence of the water on the other side basically create a further mutually stabilize the hydrogen bonding on both sides of the graphene, and it distorts more. So here the water structure is much more distorted than in this case. That's why surface tension is a bit higher. Okay, so in conclusion, we have developed a procedure to take into account surface polarizability within an MD loop. What we saw is that ions dissolve on the surface via polarization effects, but they don't dehydrate if the hydration free energy is too high. I think an interesting result is also that graphene is not a metal, but is a semi-metal, even when it's in contact with the electrolytes and even when it's charged. And the water graphene surface tension is affected by the nature of the support of the graphene. When the graphene is immersed, so is immersed in water, basically has a slightly higher surface tension than when it's supported on insulator or on a polar support. So what we're trying to do now is we are using this MDQM procedure to calculate the actual capacitance of the various ions to compare directly with the experiments. We are developing a more transferable neural network to completely avoid the QM calculations, because nothing much happens really in the quantum mechanical calculation. Fermi energy levels doesn't change and anything. And then now we are also trying to calculate this surface tension with the procedure I show you in confinement, and also for electrified surfaces to see surface tension and relate to electrowetting as well. So I want to thank the people that actually did the calculation, the 3 postdoc in the group, and Panos that help us with the neural network in IBM Zurich, Fausto that help us for the hydrogen bonding structure in the IBM UK, and Alessandro for the quantum mechanical calculation. So the European Union also for funding. Thank you very much.
Thanks, Paola. Maybe there's time for one quick question. I have a comment maybe for this SIG meeting is we develop a lot of these nice molecular dynamics tools, and this is again obviously a very important tool of how do we determine potentials starting from the quantum all the way up to the MD. It feels very important, and I wonder if we could discuss this later on of how we can translate these tools, that we can share these tools, that we can use these in the future. Perfect. This is great.
Okay. So thanks, Matthew. Thank you so much for inviting, and for the interest of time, I will be, of course, very brief, but this is a very interesting topic as such. It's evaporation of saline aqueous nano-droplets, and the whole objective is to see something beyond what we traditionally understand as the coffee ring effect. So anyway, again it's hanging, I don't know what it is. Yeah, something has happened. It's hanging. Just give a moment. I think it will be. Okay. So this is what is the so-called coffee ring effect. So if you have a spilled drop of coffee that dries on a solid surface, it leaves a dense ring-like stain along the perimeter. This is a very common experience that all of us have. And if you see how it is evaporating, it's a nice schematic from one of the seminal papers on this topic, that the evaporation rate is typically the highest near its outer rim, which in a more formal language we call as contact line. This contact line is usually pinned to the surface, which restrains the drop from shrinking. And this is commonly as a result of microscopic surface roughness and not very well understood how it actually happens. So what happens is that when this evaporative loss is taking place, the system must draw liquid from the droplets interior to replenish that. It's just a simple conservation of mass, what you can see by the red arrows. And the particles which are there in the droplet are thereby dragged to the contact line, and when the drop has fully evaporated, it will form a ring-like deposit. So this is influenced by a lot of factors like Marangoni flow or surface tension gradient driven flow. Also on the crystallization dynamics, jamming of particles, buckling of particle films at the liquid air interface. So many of these factors are actually known to control this phenomenon, and the control is via implicitly an alteration in the contact angle. And here lies the question that if the contact angle during its dynamic variation is creating an impact, then what is the role of electrokinetics and electrical double layer phenomena, which is also a surface or interfacial phenomenon. In this particular talk, I want to emphasize on a very important aspect, that is the coupling of charge and salt. So it is well known that common substrates which host droplets, micro or nanometer scales, they will have certain intrinsic charges. And it has earlier been shown also, for example, I am citing here one of the papers. So if you have, for example, like charge systems, the capillary flow inside may give ring deposits. And if you have oppositely charged systems, you can have interface trapping, and which can lead to homogeneous deposits. This is about the charge. On the other hand, there also has been recent upsurge in interest of what is the impact of salt in the droplet in terms of its evaporation characteristics. And normally the salt has a very important influence, no matter whether electrical double layer phenomenon is imperative or not. And for example, this particular recent study shows that salt will actually arrest the phenomenon, this coffee ring effect phenomenon. Now, considering the purview of this particular presentation, our job will be to see that how the electrical double layer phenomenon coupled with the presence of the salt ions is possibly going to impact this. So just for the sake of everybody who is attending this meeting, the electrical nature or electrified nature of the interface is primarily based on a phenomenon known as electrical double layer phenomenon. So when you have a surface, it so happens that in contact with an electrolyte solution, it can get ionized, and in a way that the surface itself has a net charge, either positive or negative, and the bulk of the fluid will have opposite of that net charge to make it totally a neutral system. Whether the surface will be of negative, positive or zero charge, it depends on the pH of the solution. So that is where the solution surface interface interaction is very, very important. So this is a typical example where if, for example, the droplet, the water droplet is sitting on glass with a pH of 7, the solution is there with a pH of 7, so it will develop a negative surface charge. The remaining fluid will have positive, preferential positive charge. That means some positive and some negative, but positive will dominate over negative. So in that way, a potential distribution will be created across the transverse direction of the surface, and primarily there will be a layer of ions which is immobile, which is called as the Stern layer, which you can see that it is completely immobile sitting on the surface, and you have the outer layer or the diffuse layer which is mobile, and the interface between these two layers, conceptual layers of course, is known as the shear plane, and the potential there is known as the zeta potential. We all know that zeta potential is one of the key things in colloidal chemistry. So when we are talking about the phenomenon of electrical interactions at the wall, we have to keep in mind that the phenomenon is very much different if it is a microscale and a nanoscale phenomenon. So because over nanometer scales, the size effects of the ions becomes very critical, and it is not so when we are talking about a microfluidic paradigm. So the degree of coordination of the ions with the water, which that discrete level interaction normally we do not consider or capture on a macroscopic viewpoint, but from a molecular viewpoint it impacts, and the ionic size has a very important effect on the nature of the density fluctuations at the interface. Why I am talking about the density fluctuations is because it will be very, very critical in terms of dictating the coffee ring effect that I am going to talk about. So what you can see here is that if you see, for example, two different cases. One is a surface with an intrinsic contact angle of 10 degree, another a contact angle of 120 degree. So in the latter case, addition of salt increases the fluctuations and the density peak near the wall, whereas for the contact angle of 10 degree, it actually reduces the fluctuations, and we will see why it happens. But more critically, these fluctuations are also dictated by strongly the electrical double layer interactions. The Stern layer, which we normally consider to be immobile, that is the layer of ions which is at the surface, which is encircled by the red mark here. That layer of ions is normally immobile, but with lots of density fluctuations or other forms of perturbations over nanoscale, these ions will be dislodged and their dislodging would mean that more ions are infused into the bulk flow. So when ions are infused into the bulk flow, the ion-water interaction will also give rise to a significant electromotive force on the fluid. So all in all, that possibly means that the zeta potential is no more that nominal zeta potential that we talked about, but its modification because of the Stern layer remobilization. It is also realized through slippery hydrodynamics instead of the no slip boundary condition. Now this slip, because it has a strong relationship with what is happening at the electrical double layer, so there is a dependence of, or coupled dependence between surface charge and slip. So if you plot the slip length, which is sort of a quantitative indicator of how much the fluid is slipping at the surface, at low surface charge, we can see that because the surface charge is low, it is hydrodynamics rather than electrostatics which dominate the proceedings. But if you consider the intermediate, somehow, if you consider the intermediate surface charge density regimes, so you will see that there is a decreasing slip length with increase of surface charge. Now this is something which is very critical, because the essential coffee ring effect is a function of fluid flow inside the droplet. That is a function of the combined effect of hydrodynamics and electrostatics. So why this is happening is primarily because the ions which are there at the surface, they are hydrated. So if you have more surface charge, it simply attracts more ions, and the ions are hydrated with water, and therefore water is trapped. It's a very simple way of explaining something which is significantly more complex than this. But if you go to even further higher surface charge density regimes, what happens is that the surface charge does not influence the slip length anymore. So with this background, we wanted to study the evaporation of saline nanodroplets. So this is a simulation platform that we created, and this work was done, of course, by our students, me and Professor Chirudeep Bakli, who is perhaps also sitting in this meeting. We have advised the student to perform the simulations, and this is what the simulation which was done. So the atoms were arranged in a FCC structure, and a simple, common salt. So sodium and chloride ions were added with varying concentrations, and roughly 5,000 to 10,000 water molecules were distributed over over a domain which is like 10 by 10 by 10 nanometer roughly. The negative surface charge was distributed among the surface, and negative charge was taken because this is something which is commonly replicating the standard nanofluidic interaction scenario, and the typical Lennard-Jones and Coulombic interaction potentials were considered, and the periodic boundary condition was imposed. So first we studied the ion transport inside the droplet over uncharged surface, and what we saw is that we have a net outward motion of the fluid, and it supports ring formation. And here we do not actually take into account the surface charge. So this is just to isolate the surface charge effect with the salt transport, because if ions are put, that it will be transported. Now we will see that what is the impact of the surface charge. Screen is creating a little bit of problem. Yeah, okay. So if we add salt and also add surface charge, we see that when the salt concentration is increasing, typically the contact angle is increasing over time. So the concentration alters the solid liquid and liquid vapor surface tension, that alters the interfacial energy and the contact angle increases. However, if you decrease the surface charge, so that is like instead of increasing concentration, if you decrease the surface charge, then also you see that you have the droplet spreading is influenced, and how higher spreading results in lower contact angle. So if you see here that from 0.003 coulomb per meter square to 0.054 coulomb per meter square, if we increase the surface charge, the contact angle is coming down. So it is actually the other way. I mean, I have just very mistakenly copied pasted the arrow, so it shows increase. It's decrease, but just to show it's a contrasting effect. So now, if you see the coupling, now this is where it is important. So if you see the coupling, the surface charge salt coupling, so the first thing that it does, it alters the fluid layering, and the fluid layering it is important because that is what is essentially deciding the number of water molecules that are available for undertaking the spreading phenomenon. So with the different fluid layering, the spreading phenomenon will be different, and therefore the charge salt interplay, by altering the fluid layering fundamentally, will try to have an impact on the overall spreading thing. How it, what kind of impact it has? So these are just certain snapshots. So if you are having increase of surface charge, so if you see these cases, so if you go to 0.044 coulomb per meter square. So this is a non-zero surface charge which is considered in this diagram, and you can see that it's a more of a uniformly distributed charged particles in the domain. But if you increase or if you decrease the surface charge, you will see that it is more ring type. At the same time, if you increase the salt concentration, so if you see, for example, from 0.83, you make it 1.67 molar. So what you see is that it is more like a ring structure deposition. So in a way, it is having a conflicting effect, and what it all means is that one could control the evaporation dynamics. That means the rate of evaporation, or the number of molecules of the droplet being evaporated over a period of time, how it is being influenced by charge and salt. So if you see a higher surface charge, so for example, if you look at the left view graph, so higher surface charge will have the higher evaporation rate, and it is quite clear from that diagram. But if you have higher salt concentration, it will have a lower evaporation rate. Now that is what the essential message or story from all these diagrams and graphs are, and that will have a reduction of local water vapor pressure and agglomeration of ions near the droplet periphery. So we have found out a way of controlling the deposition by using the confluence of charge and salt and their coupling. So this is a regime diagram where we plot the deposition pattern contour as a function of the salt concentration and surface charge. So we see that there is a regime where you have the evaporation rate being reduced, which is towards the top. So high salt concentration and typically low surface charge, there you will have a ring formation. Whereas towards the bottom right, you have high surface charge and low salt concentration, and it will be more of a uniform deposition. So now this is where actually possibly it got frozen. So what I just illustrated is just a molecular dynamics simulation where we put up some salt water, sodium chloride water on a surface and allowed it to evaporate. First with no effect of charge, only the salt, and we see clearly the flow. Now you put up the charge and you see what happens. So the alteration that is happening with the contact angle, and that is what is very important and critical here. It is different for increase of salt concentration and increase of surface charge. With increase of salt concentration, it increases. With increase of surface charge, it decreases. And it all happens because of the layering of fluid at the near wall regime. And this is a diagram which tries to show the combined effect of charge and salt. So if we have, for example, increase in charge, it tries to have a uniform distribution of the particles. But if you have a lower surface charge, you will simply have a greater tendency of ring formation if you have a higher salt concentration. So in a way, you have a mechanism by which, by using salt, you can lower the evaporation rate, but by using a higher surface charge, you can increase the evaporation. And because they are interconnected, so this is the regime diagram that I was talking about, that if you have low surface charge but high salt concentration, it will have evaporation rate which is less and stronger ring formation. On the other hand, towards the bottom right, if you have higher surface charge and if you have lower salt concentration, it will try to have more uniform deposition, not ring formation. So in that way, by having an interplay of salt and charge, it is possible to have a control over the pattern that you want to form. And because they are interrelated, it is not just trivial that you can consider them in isolation. Their coupling is very important. So summarily, the role of ionic inclusions and surface charge, two of the most inevitable aspects of nanoscale transport with biological interfaces, may actually open up new regimes of evaporation-driven nanoscale interactions. Liquids containing suspended particles, the particles may be from spherical to elongated, such as nanoparticles, salts, polymers, DNA, protein, etc. They may be deposited in a pattern which is influenced by both of these. And in practice, even in some industrial applications like inkjet printing, you require that a solvent dries, leaving a deposit of ink. And this is the same physics of drying that we are talking about, but there are limits to that, and possibly the charge salt interplay may be harnessed to overcome the current limits. Proteins which dry on a surface, they leave some patterns which are distinctive hallmarks of those proteins, and therefore it could open up the possibility of the very simple low-cost diagnostic technologies by using a simple drop of biofluid like blood, saliva, or whatever. So on a more sort of historical and philosophical note, more than 300 years ago, Leeuwenhoek discovered a world of microorganisms when he peered through a microscope, and the first thing that he looked into is a tiny liquid droplet. In modern times, we are talking about nanoscale droplets, and these may be harnessed to probe molecular phenomena that have by far remained to be explained. So thank you so much, and thank you for patiently listening to this. And I'm sorry there are some interruptions. Actually, I am on travel now because of some kind of emergency for which I had to come out of office. So, but thanks for your patient hearing.
Thanks, Suman.
Philip Camp from the University of Edinburgh, and he's going to talk about using NEMD to study problems in industry. Take it away, Philip.
Super. Thanks very much, James. Okay, well, hello, everyone. First of all, I just want to say thanks to Ed, James and Matthew for organising this meeting. I was at the last one in Brunel a couple of years ago. It's a shame not to see you in person, but well, do the best we can from my sofa. Okay, so title of my talk is using non-equilibrium molecular dynamics to study problems in industry, and I'm just going to touch on 4 areas where we've used a range of molecular dynamics techniques, including non-equilibrium techniques, to get some insight on some industrial problems. So the first one I'm going to talk about is molecular liquids, and specifically oils under extreme conditions, such as you would find in engines. I'm going to talk a little bit about thermal conductivity of liquid mixtures, and I want to introduce you to a new experimental technique which can be used to monitor liquid composition under extreme conditions. Then I'll talk a bit about solid-liquid interfaces, and particularly friction and how you control it. So I'll talk about surfactant-like friction modifiers adsorbed at the solid-liquid interface. And finally, I'll say a few words about some polymeric compounds that we've been looking at in the same kind of situation. So first of all, to motivate the talk, what are the industrial problems? Well, it's all about controlling interfaces and looking at molecular liquids and additives under extreme conditions. So the obvious examples are things like combustion engines, where the lubricant is controlling the friction between moving parts. But of course, we all know that the internal combustion engine is on its way out. So there are other applications where it's very important to control friction and wear between moving surfaces. So, for example, things like wind turbines, robotics, and then also, of course, electric and hybrid motors and engines. Of course, they've all got moving parts. They all need lubrication. They all need transmission fluids. These sorts of things. So, in all of these situations, we're trying to control interfaces or control fluids under extreme conditions. And so, I want to show you how we can use molecular dynamics to understand what's going on. So the first example I'm going to talk about is a molecular liquid under extreme conditions. And the first thing to say is that in engines, liquids do indeed experience very extreme conditions. So at some parts of an engine, for example, piston rings or valve trains, the transient pressures can be as high as gigapascals, or 10 to the 4 atmospheres. And moreover, they can be sheared at very high rates, up to about 10 to the 7 inverse seconds. So before we talk about the dynamics of the fluid under these conditions, what is the thermodynamic state? What is a liquid like under these extreme conditions? So the first example I'm going to talk about is squalane. So squalane is a good choice as a model kind of base oil. It's got the average molecular weight and branching of a typical base oil. And so experimentally, we've looked at this compound under high pressure. So let me just take a few minutes just to explain the experimental work. So we use a device called a diamond anvil cell. So basically you squeeze the liquid between 2 diamonds. The diamonds, of course, being transparent, so you can do spectroscopy and imaging through the sample, and of course it's a hard material. The fluid is confined by a gasket, and then so you put the liquid into this little vessel here, and then you also put in some ruby chips. And the point about the ruby chips is that the fluorescence of ruby depends on the local pressure. And so you can image the sample of liquid through the diamonds and look at the ruby chips. And on this diagram, they're highlighted by red circles. And the idea here was to see whether each of those ruby chips is reporting the same pressure throughout the sample, i.e., is the liquid, which is filling the rest of the space, is it a hydrostatic medium or not? So on the upper half of the graph on the right-hand side, plotting the standard deviation of the pressure reported by those chips. And you can see that below about 1 gigapascal, the standard deviation is practically 0. So it tells you that each of those ruby chips is reporting the same pressure. But as you go above 1 gigapascal, that standard deviation starts to increase, and it says that the pressure over here is not the same as the pressure over here. So it's no longer a hydrostatic medium. And we can extract a crossover pressure. This is all done at room temperature. We can extract a crossover pressure. It's about 1.6 gigapascals. And if I put that onto the phase diagram on the lower right here, that green cross, that's basically our crossover. And it seems to match up quite nicely with measurements of the glass transition temperature, either from thermal conductivity or heat capacity, or from the viscosity. And so that's in the metastable part of the phase diagram. The solid black line here is the freezing line from molecular dynamics simulations. So starting off from a perfect crystal and then melting it. So that's a rough estimate of the equilibrium freezing line, but there is in fact a glass transition, or something that looks like a glass transition, in the metastable region of the phase diagram. So this is interesting because this is occurring at gigapascals pressures, and that pressure can be experienced in an engine. Okay, so first of all, let's see if we can look at the thermodynamic properties. So, for example, from simulations and experiment, these diamond anvil cell experiments, we can measure the compressibility as a function of pressure. Of course, as you increase the pressure, the compressibility goes down. And the green points are from experiment, this diamond anvil cell. The black points are from our molecular dynamics simulations, either using all atom or united atom potentials. So you can see the compressibility just absolutely plummets when you get to about 1 gigapascal. Incidentally, in terms of the freezing line, I said that we're in the metastable part of the phase diagram. Well, we can do high pressure X-ray diffraction, and on the timescale of those experiments, you don't see any Bragg peaks, you don't see any freezing. So in fact, this process takes months, right? You can wait months for squalane to crystallize. So that's quite good for simulation because, of course, nucleation is a rare event. It's difficult to simulate. So we can simulate this metastable high pressure liquid, and that's what's done in the lower half here. I've extracted out the structure factor from the X-ray diffraction. Those are the points. And then we just put on top the molecular dynamics results. And you can see the black points are at low pressure, red points are at high pressure. The peak shifts to higher wave vector. That's because we're compressing the fluid. And we can track where that peak position goes as a function of pressure and say that around about 0.1 GPa, the structure starts to change somehow. And I'll say a little bit more about that in a minute. So the basic phenomenology is approaching pressures of about 1 gigapascal. This molecular fluid is basically in a glassy state. It does not crystallize. It takes months to nucleate. And so that's good to know from an engineering point of view, what the state of that fluid is. So here's where we look at the non-equilibrium molecular dynamics. So in the lower two panels here, I'm plotting the viscosity first as a function of shear rate. That's at ambient pressure. And then looking at the Newtonian viscosity as a function of pressure. Why are we doing this? Well, we tried all sorts. We've tried Green-Kubo approaches. We've tried Einstein approaches. But the SLOD NEMD was basically the only reliable way to do it. And although it takes a lot more work because you have to, at each pressure, calculate the viscosity as a function of shear rate and then extrapolate to the low shear rate Newtonian regime. It seems to be the only reliable way of doing it. And so you can see that when we're going up above about 0.1 GPa up to about 1 GPa, viscosity is just shooting off into space. And of course, that's just signaling the onset of this glass transition. In equilibrium molecular dynamics, we've also computed the diffusion coefficient. And as you'd expect, as you increase the pressure, that just, again, absolutely drops very rapidly due to the cessation of diffusion. Okay, so from the pressure versus viscosity curve, we can get some pressure coefficients. It's important to match up to experiment. So there's a couple of ways of getting this pressure coefficient. So if you assume that the viscosity increases exponentially with the pressure, you can extrapolate that. You can get that that constant. From experiments, it's around about 22 inverse gigapascals. We're getting about 17. This is from the united atom model, so we could probably improve that with a better force field. You can also, if you like, work out the area under the inverse of the viscosity to get this coefficient. And again, there's similar sorts of numbers. So it's important to make contact with experiment, both in terms of the structure, the thermodynamics, but then also here the transport coefficient for the viscosity. Okay, so the liquid is a glass at high pressure under conditions found in engines. That's the main finding. Similar sorts of results we can get for other hydrocarbon models. So, for example, mixtures of polyalpha olefins, exactly the same sort of approach. Equation of state, compressibility goes down, diffusion goes down with pressure, viscosity goes up. It's the same sort of picture. Okay, so that's the first example I wanted to talk about. Next one, oh, hold on, I'm already, time's already going on. Okay, so what's the molecular cause? It's to do with molecular collapse. As we go above about 0.1 GPa, the molecules fold up, and so we've got some sort of structural signature for this change in thermodynamics and dynamics. Okay, right, now next one, thermal conductivity of liquid mixtures. So we did some simulation work to complement experimental work in our department on a hot wire device. So what's this hot wire device? It consists of a very thin platinum wire, which we heat through resistive heating, and then we dip it into a liquid. And this is a very thin wire, only about 30 microns across, and we heat the wire over durations of milliseconds. And the idea is that depending on the medium that the wire is immersed in, different amounts of heat will be conducted into the liquid. And therefore, the temperature of the wire will change with time, depending on what the conductivity of the surrounding medium is. And so the idea is, can we use this to measure the composition of a liquid over millisecond timescales? That's the basic problem. So this is what we do in an experiment. We've got our platinum wire. We start off at ambient temperature. We pass a high current through it, so the temperature of the wire goes up. And then we turn the power down, so we turn the current down. And then what happens is that the temperature of the wire can go down because there's, over this now timescale, heat can be conducted into the surrounding liquid. And so you get these characteristic kind of curves for this particular minimum. And with increasing liquid thermal conductivity, we get a deeper minimum. And so over the time scale of milliseconds, we can measure the thermal conductivity of a liquid. That's the proposal. We need to be able to fit the experimental data, and it's complicated, but we have an initial high power pulse, a subsequent low power pulse. You can work out using the heat equation what the temperature of the wire should be. It depends on the geometry of the wire. It's a complicated function, but the key thing is that we can fit this single parameter, the thermal conductivity of the liquid multiplied by its heat capacity per unit volume. All right, so that's all we need to know. We can fit the experimental data and get this number, and that's what we're going to try and compare to molecular simulation. As far as the simulation is concerned, we're looking at quite complex molecular fluids. Again, we've tried almost every approach to calculate the thermal conductivity. But again, a non-equilibrium approach seems to be the most reliable. Here we're using the approach due to Müller-Plata. And here what happens is that you divide your simulation cell up into a cold region and a hot region, and you exchange kinetic energy between atoms at some predetermined rate. And then you measure, so that gives you a heat flux, and then you measure the temperature gradient. So you're not applying a temperature gradient and measuring the heat flux. It's the other way around. You fix a heat flux and then you measure a temperature gradient, and it's much easier to measure the temperature gradient. So this works out extremely well. It's implemented in lamps, no problem. And of course, we also need the heat capacity for this beta parameter. We get that from equilibrium MD simulations. So here's some data. Here's the experimental hot wire data showing this characteristic minimum. These are at different compositions of the liquid. Here we're looking at a mixture of squalane, which is meant to be a model of an oil, octane, which is a fuel, and we're seeing whether we can detect a difference in thermal conductivity which correlates with composition, and we can. There's obviously big changes here in these curves, and we can fit the experimental data, so those are the lines there. It's a great fit, and we can get out this parameter, which is thermal conductivity multiplied by heat capacity. So we get that number out and we plot that versus composition, and this is what we get. So the black points are from the hot wire experiment, and the red points are from our non-equilibrium dynamics, and it all looks pretty good. Okay, there's a bit of scatter of data there, but bear in mind that these hot wire measurements are done on milliseconds with tens of microns thick wire, and so this is the sort of thing that you could put into an engine or a continuous flow reaction line or something like that to monitor liquid composition in real time with millisecond resolution. So we've done exactly the same sorts of experiments and simulations with a wide range of liquids, but here I'm just giving you the oil plus fuel example. Okay, so that's a device which could be incorporated in industry. Okay, next one. So friction. So far I've been talking about bulk liquids. Now I want to talk about the solid liquid interface. And in this first example, we're looking at the sliding friction or kinetic friction of squalane confined between iron oxide surfaces at a given temperature and pressure. The reason why we're looking at these conditions is that James has done a lot of work in this area, and so we want to check that in our hands we can get the same results from our simulations. So here I'm showing the friction coefficient. So it's the lateral force divided by the normal force on the walls as a function of the sliding speed or shear rate. The black points are from experiments done by the Imperial group, and the green points are James's simulations, and so the red points are ours, and it just shows that basically looks like we're doing things correctly, and we can almost kind of connect up there with the experiments, and that's a general problem with simulations. Is with molecular simulations, it's getting down to low enough shear rates, which is the problem. Nonetheless, if we've got a protocol that seems to be working okay, we can now do some screening. So for example, we can just look at some simple organic friction modifiers which adsorb at the solid liquid interface, see how it changes the friction. So here I'm just looking at some molecules, none of which are industrially very interesting. Obviously for confidentiality reasons, I can't show you everything that we've done, but it's just illustrating that we can screen different friction modifiers and sort of say, yeah, okay, that kind of chemistry works quite well at the solid liquid interface. This last example, though, I want to expand on that, glycerol monooleate. So in our simulations, we've got molecules adsorbed at the solid liquid interface. We really want to be able to have some confidence that we're simulating that interface correctly. And glycerol monooleate is an interesting one. So glycerol monoaleate, here's the molecule. It's got a very polar head group. And the key point here is that this molecule forms reverse micelles in bulk solution. So at the bottom here, I'm showing you a reverse micelle, the polar groups on the inside, non-polar groups on the outside. And the bottom right there is the form factor, so from experiment and simulations. And there's always perfect agreement. So we're getting something like 15 or 16 angstrom radius micelles. Now we look at the solid liquid interface, and we can see from neutron reflectivity that we get perfect agreement between experiment and simulation. The points here are from neutron reflection. The lines are computed from our simulation, from electrodynamic simulation. So these are with different deuterated solvents, but basically the agreement is practically perfect. And from that we can get the thickness of the adsorbed layer from experiment, and it's roughly 30 angstroms, something like that. The red lines are from our simulation, and again the thickness of that layer is about 30 angstroms, i.e. it's about twice the radius of a reverse micelle. So this is the structure of the adsorbed film. It's not the sort of simple polar group onto the surface, tails sticking out into the solvent. It's basically an adsorbed reverse micelle. Incidentally, we're now doing experiments where we can do this under shear conditions. So we've got a kind of roller device and bounce neutrons or X-rays off that interface, and we're planning to look at the effects then of shear on these adsorbed films. Okay, so how does that correlate with friction? So this was a study where we looked at the glycerol monoaleate, and we asked, well, what happens if this undergoes hydrolysis or degradation to form other molecules, for example, oleic acid and glycerol? So that can happen in an engine. And so this plot on the right here is showing how the relative change in friction coefficient as we convert initially 10 weight% glycerol monoaleate into other products, things like oleic acid and glycerol. And the key point here is that as the GMO content goes down and the amount of products goes up, the friction coefficient goes up, and almost by a factor of 2. So this is important to know, and we can kind of rationalize that with the formation of these reverse micelles. So when we've got glycerol monoaleate, we get nice, strongly adsorbed reverse micelles. The density, this is the density profile of heptane, that's quite flat, so that it's a very fluid layer and the friction coefficient is low. But when we turn some of that GMO into hydrolysis products, we get less adsorption, and moreover, the oil in this case, the hydrocarbon, is showing a lot more ordering, and that seems solid-like ordering near the surface, and that seems to increase the friction coefficient. So here we're looking at it's the interplay here between self-assembly, adsorption, and friction. Okay, the last one I'm going to talk about is polymers. So now we can do the same sort of thing with polymeric compounds. This example here is a polyfatty acid oxazoline. So basically, it's something like a backbone of 30 of these units, and then it's got a load of basically oleate tails coming off the side. So it's a bit like a bottle brush polymer. First of all, these things like to associate in oily solution, and we know that because, again, we've done the neutron scattering. So if we do a simulation of one of these polymers, we get a form factor which looks like that dotted line. But if we now put 2 in and they cluster and we work out its form factor, it agrees almost perfectly with the experiment. So there's 3 sets of data here on that lower part of the curve there: experiment, a fit to experiment, and molecular dynamics. So it's absolutely spot on. So we know what these molecules are doing in solution. We can then put them at the interface, see how they adsorb, and they form these kind of clumps. And again, we can do neutron reflectivity, and comparison doesn't look too bad. Okay, and so then we can look at what the friction properties are like at high pressure, high sliding speed. Got the friction coefficient versus pressure, The red lines are when we've got the polymer in the solution as well. Black line is when we've just got the pure solvent, in this case it's dodecane. And again, we can rationalize that with the ordering of the dodecane with and without the added polymer. So without the polymer, we've basically got 5 solid layers, but with the polymer, it kind of softens that interface between the metal oxide surfaces and the fluid. Okay, last example. So Patrick spoke this morning about functionalized polymers with sulfophilic and sulfophobic groups. Here we're looking at a similar kind of molecule. So this is a copolymer that's now functionalized. The functional groups are solvophobic, they don't like oil. And so the question we're trying to answer here is, what's the effect of the distribution of functional groups on the backbone of the polymer with an equal functional group content? So here we're doing united atom force field, molecular dynamic simulations, iron oxide surfaces, again, non-equilibrium conditions. Let's see what happens. So here we're looking at different distributions. So the top row, this is where we've got all the functional groups at one end. Second row, we've got them split at either end. Third row, they're in the middle. Fourth row, we've got an even distribution of functional groups. And in the last row, they're random. And I've ordered these here in increasing friction coefficient and increasing viscosity of the bulk solution, which we've also measured. And all I want to point out here is that the functional groups are highlighted in orange. And if you squint at it and you just see where the functional groups are, they're clustering much more in this case than they are with a random distribution. And that seems to be correlating with viscosity and friction coefficient between these surfaces. So just by squinting at these movies, you can kind of see the structures are different. These non-equilibrium structures are different. It depends sensitively on the distribution of these solvophobic groups. And then we can correlate. We've now got a structure property relationship between architecture of the polymer and the rheology and tribology. Okay, so just to sum up, my time is up. I've given you 4 short summaries of some studies we've done, either looking at rheology, but also structure and thermodynamics of molecular liquids at high pressure, an application to thermal conductivity of liquid mixtures, friction reduction by surfactant-like modifiers, and then also how polymers control the solid-liquid interface. So last slide, just want to thank my group. These people have done all the work I've shown you in Edinburgh, all the simulation work. I thank my experimental collaborators in Edinburgh for doing the high pressure work and the hot wire experiments. Sandy Armstrong, Alex Routh in Cambridge, the neutron reflectivity. And we get a lot of support, not just financial, from our industrial collaborators at BP, Infinium, and we also get EPSRC funding. So thank you very much indeed for tuning in. And that's it.
Thank you very much. Brilliant talk. Yeah, I could probably sit and speak to you about it for hours, but in the interest of time, we've probably got time for one quick question. So if anyone would like to unmute and quickly ask a question before we move on.
Yeah, I've got one. It's David Hayes here.
Hello.
Hello. Do you find that the shearing of action changes the density profile of the additives near the boundary? Does it affect how the absorption of the species?
A little bit. So at very high shear rates, we do see there is a sort of slight molecular tilt. In the case of normal friction modifiers, there's a slight tilt, but it's not very pronounced. With the reverse micelles, then definitely they can disintegrate at the very high shear rates. So short answer is with the normal organic friction modifiers, yeah, the density profiles change a little bit, and the average angle of the molecule with respect to the surface changes a little bit. With the self-assembled structures, the response of structure is more pronounced. So we have measured all that, like density profiles and molecular conformations and all this kind of thing. But I think I was a bit surprised that it changed as little as it does.
Yeah. Oh, thank you.
I think Jesper, did you raise your hand, or was that the clapping emoji thing? I'm not sure. Is that?
No, I do have a small, quick, maybe technical question. And thank you, Philip, for a nice presentation. Really interesting. So my question goes to the Newtonian regime. So you said that you tried to reach the Newtonian regime with your non-equilibrium simulations. I've tried that myself, and I had a hard time reaching this regime with even with a molecular slot algorithm. So do you use sort of a functional form to fit your data, and then say that you end up at some point in the Newtonian regime?
So just two things to say about that. The first one is it didn't seem it seems actually easier at the higher pressure, because of course you're measuring a higher shear stress, and so your signal to noise ratio is better. The example I showed you was at ambient pressure, so that was actually the most difficult one.
Okay.
And in terms of the functional form, so the two most widely used ones is an Eyring model and a Caro equation, and actually I'm just thinking there was a sort of systematic study of that done on squalane, and I think at low pressure the Caro equation was better, and at high pressure the Eyring equation was better. Always the other way around.
It's that way around. It's Mark Robbins.
It's small. I mean, there's small changes. I mean, it's not.
But you
have to assume a function and fit it. Yes.
Yeah. Then extrapolate to zero.
Absolutely.
Yep. Okay. Thank you.
Cool. I'd love to ask more questions in the discussion session if you're sticking around, Philip. But we best move on. Sure. So our next speaker is Alessio Lavino. Looks like you're here. Could you share your screen, please?
Yes. Can you see that?
Yeah, that's perfect.
Perfect.
Great. Take it away, Alessio.
Okay, thank you. First of all, thank you to the organizers for having this opportunity to present today. I also want to say a special hi to Paola that I saw this morning presenting, with whom we had the opportunity to collaborate a lot during my PhD. So today I'm presenting this work about the study of surface topography effects on pool bowling through non-equilibrium molecular dynamics simulations. This work is done in collaboration with Edward Smith from University of Brunel, Mirko Magnini, University of Nottingham, and Omer Matar, Imperial College London. Pool bowling is an interesting problem, and it finds several applications in so many different fields. Here I'm just reporting a couple of examples. For example, the electronic industry with micro cooling devices, or heat exchangers for oil and gas industry. It is also a multi-scale problem in its nature, and this is justified by the fact that several key phenomena take place at different length and time scales. It is particularly interesting to point out that the nucleation regime is strongly influenced by the interaction between the solid and the fluid. So what we have done here, and what I'm presenting today, is basically the interaction of the solid and the fluid studied just at the molecular level through molecular dynamics. The system consists of a Lennard-Jones particle system that is here represented, where basically there is a tetrahedral solid wall represented here in gray, heated up from the bottom through a constant temperature heat source. The wall, in the wall we have introduced a cavity, a rectangular shaped cavity, characterized by its width W and its depth H. And we have studied the effects of this cavity size in terms of the aspect ratio, here defined as the ratio between the width to the H, the depth of the cavity. I just want to clarify that the depth has been kept constant, so the distance between the fluid and the heat source is always the same, and so we have varied the width of the cavity itself, in combination with other parameters, which are the wettability, by just tuning the Lennard-Jones parameters, and the wall superheat, here defined as the difference between the average temperature of the wall, here represented in gray, and the saturation temperature of the fluid, here represented in pink. I will leave the computational details on the screen. I just want to point out that we have used LAMPS as a software to perform our simulations, and that we have investigated a wide range of cavity sizes, going from 0.25, which means very narrow, very narrow cavities, to 2, which means very wide cavities. Everything is expressed in terms of Lennard-Jones units, but of course there is a straight relationship between Lennard-Jones and real units. The third solid wall was imposed thanks to a spring force. Looking at some results, I start from the dynamic evolution of footballing, and here I'm reporting just a few cases to point out some interesting aspects. The first one is what here is encircled in these red circles, basically, which is the comparison between what happens at constant aspect ratios in the case of hydrophobic walls on the left and in case of hydrophilic walls on the right. It's interesting to notice that even when the cavity has the same shape, so the same size, by just changing the wettability of the wall, the nucleation event is completely different. Here, in the case of the hydrophobic wall, the nucleation is very well driven by the cavity post, so the nucleation site is very well controlled. On the other side, the nucleus or several nuclei may appear in the bulk of the liquid. And this is an unwanted effect because you have a poor control on the nucleation side. But on the other side, by increasing the hydrophilicity, so by increasing the wettability of the wall, a nanolayer forms near the wall itself, and this is positive in terms of heat conduction, whereas in the cases of hydrophobic walls, this does not happen, and the cavity is completely full of vapor, which hinders the heat conduction. So it's always a sake of balance, it's always a sake of trade-off. We have also estimated the nucleation time, so it's the time at which a nucleus, an embryo, appears above the apparent flat surface of the solid wall, in function of the delta T wall, which again is the wall superheat. Everything is expressed in terms of Lennard-Jones units, and the results of the MD simulations are here reported with discrete symbols. At different aspect ratios for the hydrophilic case, as an example. It's interesting to notice that the predictions of the MD simulations can be fit quite well by classical nucleation theory based model. So basically, by starting from the nucleation rate, which can be expressed in terms of a prefactor term, which accounts for collisions, and an exponential term, which accounts for the thermodynamics of the nucleation event, it is possible to express this relationship in terms of the parameters that we are using, namely the aspect ratio, the delta T wall, and the wettability. Here I'm omitting the details for the sake of time. And by just inverting this proportionality relationship, it is possible to have a functional form for the nucleation time that fits quite well to the MD data. We have also measured the heat transfer performances in the cavity. Here I'm reporting an example on a neutral surface. In terms of heat flux and temperature profiles, space averaged inside the cavity domain. As you can see, by just changing the aspect ratio, so by just changing the cavity size, the heat conduction takes place in very different way, as demonstrated here by the heat flux, the probability distribution function related to the heat flux, and the temperature profile. It is also interesting to notice that a comparison with a very simple 1D Fourier's law-based model is possible. And here we have noticed that after the nucleation event takes place, which means more or less from this time scale onward, a simple 1D Fourier law-based model can predict quite well the trend in terms of temperature evolution that we have measured in DMD simulations. Whereas when the phase change is taking place, molecular interactions are represent the predominant step, and so such a simple model is not sufficient to describe what is happening here. And this is quite expected, also in agreement with previous works. It is an interesting result in the perspective of a future link with upper scale models in a more general multi-scale modeling approach. We have also summarized in a sort of phase diagram what we have observed during our simulations. Here, this is a representation at constant wall superheat, where basically common behaviors are enclosed inside the same color line. And it is quite visible how by changing the wettability, for example, here reported on the vertical axis, or the cavity aspect ratio here reported on the horizontal axis, different behaviors are obtained. And depending on the condition, you may have a good control on the nucleation site, as reported here, or a very poor control on the nucleation site, as reported here at these conditions. The last result I want to show regards the system size. And on the first row here, I'm representing the current system size that we have presented in this work and published. And on the second row, there is a system which is 3 times bigger in X, Y, and Z. It is interesting to notice that whereas in general the behavior is quite different and so is affected by the size of the system, the nucleation event is quite comparable in terms of time scale. Whereas if somebody is interested to study the growth of the nanobubble, it is mandatory to move to a much larger system to capture more physical behaviors. We leave the conclusions on the screen. I just want to stress that current work is moving into the direction of studying real fluids, water and platinum surfaces, also silica or copper surfaces. This is in the perspective of building a direct link with an upper scale model, which will be a CFD-based model. And this will allow us to build up a multi-scale framework in order to study the different boiling regimes and not just the nucleation regime as we did here, in order to inform the experimental setup to obtain a good optimization of surface topography for boiling applications. Thank you very much for your kind attention.
Thank you very much, Alessio. We probably have time for 1 or 2 quick questions. If anyone would like to raise their hand or just unmute yourself. I've got a quick one just to start. You say you plan to move from studying kind of Lennard-Jones fluids to realistic water on platinum and other systems. What similarities and differences do you expect for these more realistic or relevant systems compared to your Lennard-Jones ones that you've done so far?
Yeah, first of all, it will be the first difference is that with water molecules, with water models, you will have electrostatic interactions that here we have neglected. So maybe this can be a first step to assess how important electrostatic interactions can be in the boiling process. Despite here, of course, this is classical molecular dynamics, so charges are static, but still you have a dipole moment related to the water molecules. And in the pure Lennard-Jones system, you can see this effect.
Thank you very much. And James Brittles has got a question, I think, if you'd like to unmute.
Hi, Alessio. Nice talk. I was just wondering what the main components are here that require molecular dynamics rather than just, say, classical CFD, because you showed some results with classical nucleation theory showing good agreement. So is there something which you need MD for here? Is it like some very thin films or something which CFD couldn't capture?
It's basically related to the nucleation event. That basically in CFD or continuum scale model, you need to trigger with some assumptions or closing mathematical frameworks. Here, this is just a consequence of the interaction between molecules. So the system evolves spontaneously towards this event. And so maybe you need a tool that is able to predict a sort of probability that this event is going to happen in that spot, those specific conditions, to inform the CFD.
So is it a density fluctuation or something that you have in the MD or something like that?
Yeah.
Okay, thanks.
Thank you.
Thank you very much. So yeah, it's probably time to move on to the next speaker now. So yeah, our next speaker is Ozgur Yazaydin from UCL.
Hi everyone, just let me share the screen. Yeah, can you see the screen?
Yeah, perfect. Yeah, if you could just make it full screen.
Sure.
Yeah, brilliant. Yeah, take it away.
Okay, great. Good afternoon, everyone. And first of all, thanks to the organizers for the opportunity. I'm going to start my timer here. Okay, so my talk is going to be about the concentration gradient-driven molecular dynamics method that we developed a while ago to model gas and liquid phase separation in membranes. Right, so we are chemical engineers. I'm a chemical engineer. I teach in the chemical engineering department. So we are interested in separations, and in this case, we are interested in membrane separation processes, which are employed in several industries. But what perhaps one thing that you might easily remember is the desalination, the reverse osmosis process, and then natural gas purification that can be, for instance, done in offshore platforms. So why are we interested in doing NEMD simulations for simulating separations in membranes or permeation of fluids in membranes? Because permeation in membranes is a non-equilibrium process driven by one or more gradients such as concentration, pressure, temperature, or a combination of more than one of them. But in principle, actually, the diffusion, the permeation is driven by the chemical potential gradient, which is a function of these terms. So this fact needs to be embraced in the simulations, and then people have been doing NEMD simulations of mixture separation or permeation in membranes for a long time, and they've been employing different procedures such as impermeable moving walls, applying brute force, or even using some hybrid methods for such simulations. I'm going to give some information about each of these approaches, and then talk about some kind of their drawbacks. For instance, one common method that is used to simulate mixture separation in porous membrane is, okay, you create a mixture and you push that impermeable wall. So you push the fluid to this side, and then you observe the separation, and you characterize the separation performance of the membrane. The problem with this method is, one, you run into feed depletion. That is, you push the fluid to the other side, and then the simulation stops. So you cannot really run indefinitely long simulation. That basically is a limitation. The other one, perhaps more serious, is you cannot control the composition of the feed size, because say one of the components is diffusing faster, so that means that the slower diffusing component is accumulating here. So this basically means that you cannot achieve steady state. The feed depletion problem actually has been rectified by removing these walls, but then simply applying a force. And then this way the fluid can circulate around the periodic boundary condition. But still, although this works for a pure component, with a mixture this will not work, because again, the slow diffusing component would accumulate here, so you won't be able to control the composition. There is actually, in principle, a correct solution for this problem, that is to use hybrid methods such as dual control volume ground canonical MD, in which you control the composition by doing Monte Carlo simulations in two control volumes. But this becomes problematic, especially if you are dealing with a dense fluid, because then insertions have a high rejection rate. So we thought about addressing these issues such that we don't run into feed depletion problem, and then we control the concentration of the species on the feed side, and then we achieve steady state truly by running by having the ability to run indefinitely long simulations, and then we want to do this without coupling MC and MD. So here's how we did it. So there is a membrane, and then you have the fluid molecules. So the idea is to control the concentration of the fluid or the gas mixture in these control volumes. The way we do it, in a very tiny region, we apply two bidirectional bias forces. The way they work is, so we have the target density, and then we have the instantaneous density, depending on the difference. So if you're undershooting the target density, the force slowly helps push molecules towards the control region. If you're overshooting, if you're over the target density, then the force acts on the opposite direction, and then slowly moves, helps the molecules move away from the control region. So, back then, so we thought about, okay, how do we implement this? And then back then we realized that the Parinello group in ETH had developed a plugin for an entirely different reason, to simulate crystal growth, which we could actually, with some modification, use it. So we collaborated with them. We took their code, made some small modifications, and then we did the simulation. So I'm going to show you how these simulations work. So I click on, hopefully this will work. No, it won't work because I'll probably need to switch to, oh, okay. Okay, yes, you can see, so we implement high concentration here and low concentration here. So because of the concentration gradient, the molecules moves toward this side. One thing that I would like to reiterate, we are not pushing molecules towards a particular direction. We're simply controlling the concentration in the control volumes, and it is the concentration gradient that is established that facilitates the move from one side from the feed side to the permeate side. So at the end, for instance, we did this for different gas molecules, and then you can see the algorithm actually maintains the concentration in this is the inlet control volume, this is the outlet control volume perfectly, though there is some fluctuation. This is fluctuating around the mean values. So we put this into action. So I'm going to in the remaining time, I'm going to give you some examples. For instance, this is the separation of a ternary mixture. And if you look at the literature, even the simulation, NEMD simulation of a binary mixture is rare. I haven't been able to found more than 10 myself. So ternary mixture is very, very rare. But then we did the simulation, we did the separation of hydrogen from this mixture, okay? And then you can see, although this is a ternary mixture, the algorithm maintains the concentration of the mixture in the inlet side perfectly. And this is the outlet side, which is usually vacuum or close to the atmospheric pressure. So we published this in a few years ago. The key thing that we learned when we calculate the flux from the CGD-MD simulation, that is concentration gradient molecular dynamics. So we calculate the flux by counting the number of molecules that goes through the membrane, divided by time and cross-sectional area of the membrane. That you divide that by concentration gradient, you get permeability. And then when you take the ratio of the permeability, that will be the selectivity. Regardless of the membrane force field that we use, we always got the correct, consistent selectivity. We know that this membrane, this Cepheid membrane, is hydrogen selective. But what if you try to compute this from a method that rely on equilibrium MD simulation? Here's what happens. So in this approach, you rely on, it's based on solution diffusion approach. The diffusion coefficient comes from equilibrium MD simulation of a periodic structure. And then if you calculate the perm selectivity, then actually the EMD-based approach fails spectacularly because the predicted selectivity is reverse selectivity. So this is a material that we know hydrogen selective, but if you rely on equilibrium MD, actually it gives you reverse selectivity. So this is why we should be using NEMD simulations for accurate prediction of selectivity in membrane simulations. Another thing that we looked at was to reveal the importance or quantify the importance of interface effects in composite membrane. So in a composite membrane, you have the crystalline phase and the polymer phase. The crystalline phase is sandwiched between the polymer phase. Often people rely on the predictions. They try to predict the composite membrane performance based on the performance of the individual components in their pure form. But then again, by doing this CGD-MD simulations, we reveal that what I'm showing you is basically the Z density distribution of methane and hydrogen mixture across the membrane. But the important finding of our paper, which we again published last year, was that you cannot simply predict the global performance of a composite membrane based on the performance of the individual components separately. So in this case, this is the PIM1 polymer and then Zifate crystalline phase. So they are not. This is not additive because of the interface effects. And in the CGDMD simulations, we were able to quantify this. Finally, I have shown you examples of a gas, but then we were also able to use CGDMD method for liquids. In this case, this was purification of ethanol by ethanol, which relies on usually distillation, which is very expensive. Rather, the alternative is use a hydrophobic membrane and do the separation in a single step. For this one, ideally, you would need a crack-free, durable membrane. But would that be the only problem? Is there a fundamental problem that needs to be addressed? Sorry, yes, my time is up, and I'm wrapping it up. What we have shown in the simulations that the hydrogen bonding is very important. I'm going to explain in the next slide and finish. The hydrogen bonding between water and alcohol molecules and these OH groups on the surface are actually playing a major role. So when we did this simulation, so this is the mixture or pure water or pure alcohol. So in the pure simulations, water did not diffuse because this is a hydrophobic material. Plus, on the surface, the water did strong hydrogen bonding with the surface. But then, when we did the mixture simulations, we observed that water actually diffused and the flux of methanol or ethanol decreased. What we found was that the hydrogen bonding between water and alcohol molecules were stronger than the hydrogen bonding between water and the surface silanol groups. That is, the alcohol molecules literally drifted the water molecules with them through the membrane. This basically reveals that even if we are able to manufacture a defect-free, crack-free, the most wonderful membrane, it may not be possible to fully separate alcohol from water. Okay, so just to finish, and then we published this very recently in Journal of Molecular Liquids, the role of hydrogen bonding in the dehydration of bioalcohols in hydrophobic evaporation membranes. So to summarize, CGDMD, I'm just going to leave these on the screen later, but by CGDMD simulations, we think we address the shortcomings of previous methods, and then we can compute steady state fluxes, and then we can characterize selectivities, and most importantly, we can understand at the microscopic level how specific interactions affect the global separation performance of the membrane. The code that we use is freely available, okay? And it can be used with Glomax and LAMPS, and then you can download it as a plumed plugin, okay? You can download it here, and there's plenty of examples if you'd like to do. I would like to thank my postdocs and students and my colleague at UCL Chemical Engineering, Matteo, with whom we maintain this website, and finally funding from Leverhulme Trust and EPSRC, and I'd be happy to take any questions. Thank you very much.
Thank you. Really interesting talk, and great that you've made your code available for others.
Yes.
Yeah, really nice. We probably got time for one quick question, I think. Yeah, I can ask one. So you mentioned that for EMD, you actually get the reverse selectivity for one of these membranes.
Okay.
Do you have any idea what the kind of molecular mechanisms leading to the catastrophic failure are?
That's actually a very nice question, and because this approach relies on the fact that the fluids must not be interacting with them strongly, but this is often ignored. So when you have a mixture like this, hydrogen, carbon dioxide, nitrogen at a high pressure, okay, actually your gas molecules are interacting strongly. Now, if you follow this approach, you're basically violating the assumption behind this approach. Whereas in the NEMD approach or CGD-MD approach, we are explicitly representing, taking the interactions into account. So that's the reason. Unfortunately, many colleagues in the literature uses this. Sometimes they get lucky, and then they report, yes, they report the results look correct, but fundamentally the approach is wrong. And this is one of the cases where we were able to highlight this. Yeah, no,
it looks like really powerful approach. So very good. Right, we better move on in interest of time. Thank you again. So our final speaker in this section is Jesper Hansen, who's going to talk about nanoscale polarization. Go away.
Okay, thanks a lot. So I too wish to thank the organizers for organizing this really nice conference. I think it's important that we, as a community, we actually see what we do. So thank you for taking time to actually organize this in your busy schedule. I have allowed for a lot of questions at the end. And also, in case you have any questions during my presentation, you can just interrupt me. I think we can just maybe raise a hand, and if I can ask someone to interrupt me, then I'll be happy to answer questions while we on the go here. Right. So I will talk about nanoscale polarization today, and it's actually an old project that I worked on, I think 5 years ago, but I think it's really well suited for this workshop. So I thought I will bring it back up. It's a project that I did sort of on the side, so I have no one else to blame. So that's why it's only my name on the first slide here. First of all, I would like to show you a result which is due to Paola and Hansen. And yeah, I should say this is the famous J.P. Hansen and not me, so I have nothing to do with this as such. But what Paola and Hansen did was that they studied a dielectric material confined in a slit pore. So they have two parallel walls, and they had a dielectric material that is composed of simple dumbbell molecules or microscopic dipoles, such that each bead had a charge, an opposite charge, thus a microscopic dipole. They applied an external electric field to the system, and then they measured the dipole moment density or polarization. I will make no distinction between those two words as a function of distance away from the wall. So on the x-axis down here, on the first axis, I have the distance to the wall, and on the y-axis, I have the polarization or dipole moment density. So what really intrigued me here was to see the extremely large variation in the polarization. And every time I see gradients like this, I feel that there should be some flux associated with this gradient. So this sort of triggered my study into this a little bit further. But taking one step back, I tend to do this, keep things as simple as possible. I wanted to do a simulation of my favorite water model. And my favorite water model is the SPC flexible water model. Why it's my favorite is basically because it's easy to implement, and it has some pretty good properties under ambient conditions. So anyway, I'll take my favorite water model. I'll simulate ensemble of these molecules at ambient conditions using just standard techniques, standard MD techniques. Then during the simulations, I calculated the dipole moment density, the polarization P, and for use a little bit later, I will write the polarization as the mass density times the dipole moment per unit mass, P. And microscopically, the microscopic definition of this macroscopic property is simply this instantaneous microscopic description, where we sum overall the microscopic dipoles or molecular dipoles, and then multiply it with the distribution delta function here. I can, rather than looking at the polarization in real space, I could look at the Fourier coefficients. So taking the Fourier transform, I basically just get the Fourier coefficients given by this sum here. So it's just the exponential function rather than the Dirac delta. So I can choose a simple wave vector to, again, keep things a little bit simple. And if I do that, I can define a transverse dipole moment autocorrelation function. So I take the x component of the Fourier coefficient of the dipole moment density per unit mass, and I simply form the autocorrelation function for this property here. So this is just the autocorrelation function of the x component of the dipole moment. I will call that C, that correlation function. So I'll calculate this runtime as I perform my standard empty simulation of my water molecules. If I do this, I end up with some correlation functions that are functions of time and wave vector. So on the x-axis I have time, and on the y-axis I have the this correlation, normalized correlation function plotted for different wave vectors. And the blue data points here are for zero wave vector, and the red data points are for the highest wave vector I studied. So this arrow here indicates increasing wave vector. So already now, one interesting thing is can be observed, namely that for k equals 0, this autocorrelation function relaxes to 0. So that actually implies that the polarization is not a conserved quantity, which is something we must take into account a little bit later. So rather than looking at the correlations in time domain, it can be informative to look in the frequency domain. So I will take my correlation function and I will do a Fourier Laplace transform of this, and I can look at the imaginary part of that spectrum, and that will give me a peak frequency. So I can plot this peak frequency as a function of wave vector. If I do this, I get the following figure here. So on the x-axis, I have the wave vector squared, and I have the peak frequency on the y-axis. And what we see is that for zero wave vector, I have a peak, which is consistent with the fact that this is a non-conserved quantity that I'm studying. And then it's linear with respect to k squared. So this is actually a fingerprint of an underlying diffusive process. And this is something that we somehow must understand. And when I say we must understand this, I mean we must have a model for this. So this is the next step I will go through. How do we model this? So in order to do this, I will try to write up the balance equation for the polarization, or the dipole moment density. So in the limit of small wave vector, I can write up the dynamics of the Fourier coefficients of the polarization using the so-called microscopic hydrodynamic operator, which acts on the microscopic quantities that defines the macroscopic quantity. So basically, if I just rewind a bit, I will basically just take this and I will differentiate that with respect to time. And then I will take the limit of small k. And this is basically what I'm trying here. And I can write out h, of course. This is pretty uninformative as it stands. So if I write out my operator, you can see it's a linear differential operator acting on the microscopic dipole mu. So here we have the differential part of the operator. Here we have the thermal part. Ci here is the thermal velocity or peculiar velocity of the molecules. And this, just to remind you, represents, I think Carl called it the dyadic. It's also, some people like to call it the outer product. So this is a tensor. And likewise here we have the advective part. So this actually describes how the microscopic dipoles are carried along the bulk fluid flow. So this is also a tensor because it's an outer, it represents an outer product. I can rewrite this a little bit. So I have so I can use Euler's rotational formula, and I will end up with a term here which is independent of K, which is important. So it's independent of K. And you can see this omega I here is the angular velocity of our water molecule I. So the somehow the dipole moment interact or couples with the mechanical properties of our fluid. Then we have the advective term here, and we have a third term here, which is a polarization flux tensor term. So from this we can infer, if we look, we can infer the dynamical equation for the balance equation for the Fourier coefficients for the polarization into, and we can decompose it into three terms: the mechanical coupling term, the advective term, and a flux term which is due to the thermal motion as well as the mechanical coupling to the, the coupling to the mechanical properties of the fluid. So this is in Fourier space. In real space, we can then write it as these three terms, these three last terms in the last equation here. And I've allowed myself to add the biterm to our polarization dynamics. E is an external field, and psi E is the electric susceptibility, and epsilon naught is the permittivity of vacuum. So this is basically just the Debye relaxation mechanism. In case we apply an electrical field, this will result in a certain polarization, as we know. So I have now the dynamical equation for, or the balance equation for the polarization, or the dipole moment density, if you like. This is a little bit frustrating maybe the first time you look at it, because you would think, oh no, I need to then include the dynamical equation for the angular velocity, and I also need some relation between the system forces and this polarization flux tensor here. But if we look at the fluctuations, and that's basically what we did in the first empty experiments we did, we can disregard higher order in the fluctuations. So this mechanical coupling term can be ignored. We don't have any advection in our system because this is done in equilibrium. This is also a higher order in fluctuation, so this also goes out. We don't have any external electrical field acting on the system, so that basically renders the problem much more simple. However, we still need some constitutive relation for the polarization flux tensor here. I should say, when I derived this the first time, I was very happy, of course, but our forefathers, they don't leave much for us to do. So, of course, this equation was not exactly in this form, but it was derived by Dahler and Screwen many years ago from a pure macroscopic viewpoint. But just to also underline that this is the balance equation for the polarization. Right, so the polarization flux tensor is not symmetric in general, but let's just assume for now that it is symmetric. It doesn't matter for the result anyway. And we can then be inspired by the constitutive relation for the pressure tensor or the momentum flux tensor. So we can write this polarization tensor in terms of a trace part and a symmetric traceless part. So this is basically just completely inspired by the Newtonian constitutive relation here. So these two coefficients are then transport coefficients. If I substitute this into the balance equation and we look at equilibrium, where we can disregard higher order fluctuations, I end up with a equation for the dipole moment per unit mass, and I'll only extract the x component, as this is the one that we're interested in. So I end up with this differential equation here. So I wanted to form the correlation function, the autocorrelation function, because that's what we could measure with MD. So multiplying with the complex conjugate x component, I can get this dynamical equation for the correlation function. And I have now introduced a kinematic transport coefficient, simply which is simply this chi-t divided with the average density. The solution to this is a nice exponential function, and it has the exponent has two terms, one which is k independent and one which is k dependent, and k square dependent. And of course, it's k square dependent because I sort of put that in my constitutive relations, in my constitutive relation up here. In any case, if I have this now, this is my model for my correlation function for the dipole moment per unit mass. So this exponent here gives me exactly the dispersion relation omega peak that we saw in the second slide I presented. So the fact that at k equals 0, there is still a relaxation, which I said was due to the fact that the polarization is not a conserved quantity. This is basically just this 1 over t, or sorry, 1 over tau relaxation term. So this is a term, which is the bi-term, so tau is the bi-relaxation time. So it's basically the relaxation of the thermal relaxation of the microscopic dipoles that we see here. This is something we can measure in experiments, and has been done many times. But we also have this k-square dependence, and if we look at the data from our MD simulation, I can fit a value for the transport coefficient mu t here, which is 2.9 times 10 to the power of minus 9 meters squared per second. So this is really close to the self-diffusivity of water, actually. So in this case, there is something that tells me that the k-dependent decay that we see is simply due to the water molecules diffusing around in our system. So they will, if there is a gradient in polarization, that gradient will disappear due to the self-diffusion of our water molecules. Okay, so I will have an application of this, which also relates to the results that Bollenegger and Hansen they showed. So I will have again a box of microscopic dipoles, or I have a dielectric material. I have no walls, but I will apply a sinusoidal electric field to my system. It's fictitious because I assume that it does not induce a magnetic field. So this E field is not associated with a magnetic field. If you like, we can also say that we put on the field for a short time and assume that our relaxation time tau is sufficiently large such that it quickly relaxes, our system quickly relaxes to the field, and then I turn the field off again, and I keep repeating this experiment. In any case, if I apply this external electric field to my system, I will end up with this differential equation here. So this is a second order differential equation, and it's a boundary value problem that I can solve. And I've highlighted the diffusion part with red. So I have some boundary conditions that I can apply, and then I can solve this differential equation here. and giving me this result down here. Again, if I did not have diffusion included in my modeling of this, I will basically just have this prefactor here, epsilon naught chi e naught, and with the sign function here. But there is an additional factor that we need to include when we include the diffusion. So this beta here is 1 over my polarization diffusion coefficient, if you like, times tau. So if I now try to take this thought of experiment and try to do a non-equilibrium simulation of this, I will get the following results. So on the first axis here, I have the system Z coordinate. So I am applying a electric field acting in the X direction, varying in the Z direction here. So if I did not have diffusion of polarization in my system, I will have the blue line here. So this is the prediction without diffusion. Oops, sorry. What I do measure is the field symbols here. So what I can do is I can calculate tau and t, and I can then predict the correct amplitude AN. So my prediction is actually, for some reason it doesn't show here, but in the first version I did of the talk, there was a small red line here. So the predictions are actually from the model is in good agreement with my NEMD results. So what we can do is that we can then try to estimate what is the effect of this diffusion. So again, remember that the amplitude, in case I had no diffusion, would just be this denominator up here, and I can divide that with the with AN, my actual measured or predicted amplitude, minus 1 because it's the relative difference. And if I do that and I rearrange my equations a bit, I can see that this will actually give me my wave vector squared times 1 over beta here, so which is mu t times tau. So we can see in case we didn't include the diffusion, there would be no effect from the diffusion apparently, but we can also see that the effect of the diffusion goes as k squared. So as we approach the, if you like, hydrodynamic limit of k goes to 0, the effect of this diffusion will be extremely small and disappear eventually. So we can test this again with for this dielectric material. This is just a simple dumbbell model in our case, and I have plotted that in the right hand figure right here. So we can see that it fits really nicely with the predictions, the NEMD data. I can then, because I know the transport properties for my water, I can also predict the amplitude reduction for my water, and I've listed a result here. So if I have a wavelength of 2.6 nanometers, I will get a I will get a reduction in the polarization amplitude of around 10%. So the take-home message here is that the polarization is reduced compared to what we would traditionally think, simply due to a diffusion of polarization. And with that, I think I will stop. So thank you for listening.
Thank you very much, Jesper. I think we've got a few minutes until the scheduled discussion/break. So if anyone has got any questions, please raise your hand or unmute. We've got one from Maxim. Maxim, if you'd like to unmute.
Can you please explain how did you get k-squared term when you're doing microscopic equations for this dipole moment? Because it seems to me that you have terms without k at all and first order in k. So where this K-squared term came about?
Yeah. I think maybe I should open my screen or share my screen once again here. That's okay.
Mm-hmm.
So it comes about, and there are two sources for this. So the balance equation for the polarization, which is the last equation here on slide 3, you can see I have a tensor I call R. So this is the polarization flux tensor. I then assume, I propose a constitutive relation for this polarization flux tensor, and I'll just switch slides now, and it comes in here. So this is my R tensor, and you can see here I have a gradient in my dipole moment per unit mass. So I have a gradient there, and I have a divergence here. So that will give me something second order derivative with respect to my dipole moment.
I see, but there is no K-square on the top of the previous slide. So how come it's possible?
This one? So yeah,
well,
so
in the top part of the screen there is only K. Yes.
Yeah. So here I have K. So 1 minus K dotted with this tensor here. That gives me, that's the Fourier transformation of this divergence down here.
Okay, I see. Thank you very much.
Okay, thank you.
Are there any more quick questions before the discussion? If not, maybe we thank Jesper again, and then Ed, I'm not sure what we want to do for the next discussion session. Maybe you want to.
Can I just say something, James?
Yeah.
I am on a Linux machine and I cannot access Brunel as a guest.
Okay, I don't know. Ed, should we just stay in the main room, or what do you reckon?
Yeah, so I'm fine with just staying here.
Yes, okay. So Jesper definitely need to stay in the main room. And then the other speakers in the session could potentially go to the discussion rooms if that's possible. I'm just checking. I had a list of people who could and couldn't leave between rooms.
Unfortunately for me, the discussion room doesn't work. So I'm just here if anyone wants to ask a question. I'm just going to stick around.
Okay.
Yeah,
no, I mean, to be honest, I think there's an advantage to having kind of panel discussion anyway. So obviously feel free to do that. Yes, the problem is it's difficult to know if someone wants to ask a kind of question, but not in front of everyone. So I don't know. I mean, it is possible to directly message the speakers. You can actually click. I mean, again, it depends if you've got access, but you can bring up a list of participants and write a message to the speakers. So if anyone wanted to do that, that's a good way to ask a kind of question, sort of more privately instead of in front of everyone. But if not, I mean, do we have any general questions for the speakers? Anyone has anything they were going to ask before? I know, and again for the speakers from the last session as well, because anyone who's still around, I reckon Suman might have gone just because it's quite late in India now. But yeah, I mean, I think
if I might have a question to Ozgur. Very nice talk from UCL.
Thank you.
I'm Sig Karbassa from Queen London. I believe my former PhD student works for you.
Yes. He's
I have a question. Hopefully you are still happy with him. I have a question on, so in your method, effectively you have you are prescribing a certain concentration.
Correct.
As far as serotonin around of the membrane, and by doing so accurately, you can actually control the diffusion through the porous membrane. Have you thought about controlling not just the concentration, but also maybe pressure and some velocity properties? For example, well, I know that perhaps the mean flow is 0, but the thermal velocity of fluctuations could be important also. So
yes, I mean, we thought about this, but when it comes to separations, it's usually what matters is, from an application point, is the composition of the mixture. So that's kind of more important for us. When it comes to pressure, what we did was, if you're dealing with a compressible liquid, we can relate the density to pressure, numerical density of the fluid in that control volume to pressure.
Equation of state, I presume.
Yes, exactly. So that's kind of how we get away with it. But is it, I mean, very precise? Obviously, no. I mean, obviously you could, one can compute the local pressure or try to control it. But again, our application is kind of geared towards the separation of a mixture, binary ternary. So what we mostly care is concentration. So we thermostat the membrane and the fluid separately. So we kind of have a good control over the temperature, and then we also have a very good control over on the concentration of the mixture. And then from there we kind of relate, to pressure within that control volume. That's what we do.
And then related question: when you control the concentration, have you made sure that you have the reservation of the conservation laws? So you cannot just arbitrarily control concentration to some value, right? You need to make sure that you're in the macroscopic sense, you're conserving mass, for example, and perhaps momentum as well. Have you checked this?
No, the ensemble that we do is NVT.
Well, this is not about molecular dynamics. This is more about controlling the mass which is coming in and coming out from control.
Oh, hold on. The mass is conserved. The mass is conserved. If that's basically the number of particles in the system is same. Is that what you're asking?
Yes, because if you are prescribing a certain concentration, I guess you need to be doing this carefully, right?
No, but I think you might mean I might have confused you, or perhaps there was a misunderstanding. But I can, if it's okay, I can share my slide again, and then
yeah.
That's relevant. So I talked about this approach, which is the hybrid one. Sorry, I messed up, but which is the hybrid one. Okay, here the particles are created and destructed, but we are not following this approach due to problems with coupling MCMD. Ours is, here you have the system, and then so let me just, for instance, yes, right, okay. Oops, I'm trying to pause it, but any particle that flows through the membrane again goes through the boundary and goes back to the feed. So overall, the number of particles are conserved.
Yeah.
We have these in this very tiny regions. We have this forces, and the thickness of this region is usually less than 1/100 of the entire system. So it's very slightly intrusive. And then the forces, and then the force can act in this way or that way.
Are those forces conservative? So if you integrate them over control volume, they will basically give zero.
Okay, I don't have the answer for that for you. Yeah.
Okay.
Okay.
Anyway, very interesting. So actually, one maybe a small remark is that you may have a look what we've done with the two-phase flow analogy, and this is what FAN has been working on.
Yes.
We're trying to make sure that the conservation is preserved quite accurately.
Okay. All right. Thank you.
Thanks.
So I'll just stop it.
Ozgur, I also have a question actually for you.
Okay.
Yeah, so I would suspect that momentum is not conserved for what you're doing, but I don't think it's too severe. As you say, I mean, you impose some sort of thermodynamic force, and the way you impose it happens far away from what you're actually interested in. So I think maybe that's okay. I have another question though, but I do agree with the previous question that is something one should always be careful with. So you talk a lot about concentrations and permittivity, but what about, shouldn't you talk about chemical potential really?
Okay, so again, yes. So I'm going to, let me share my screen again.
Yes, sure.
So how do I do this? Okay, there you go. So again, I referred to this. By controlling the density here, okay, and here, actually, although the method is named concentration gradient driven molecular dynamics, I kind of talk about the Michel Parinolo's work, because we actually we relied on a method that developed that they use for crystal growth, in which they actually maintain the chemical potential external to a crystal. Okay, so but actually it's a paper by Claudio, Matteo, and Parinello. And if you go to this paper, there is a citation, and then and actually in that paper they show that with this method, the chemical potential in these control regions are maintained. Okay. However, as I said, it's because this is kind of application, geared, for membrane separation, separation of mixtures and membranes. We thought we kind of renamed this approach concentration gradient driven. But again, I'm going to have to refer you to that paper which we cite in this one by Perego, Salvolagli, and Parinello, and then they actually show that the chemical potential is maintained in the control volumes. And you're right. Although, again, for practical reason, chemical engineers talk about the concentration gradient in mixture separation. The truth is the diffusion here is driven by the chemical potential gradient.
Yeah, exactly.
And originally, as I said, in their paper, they show that the chemical potential is maintained in the control regions. Yeah.
Okay, thank you.
Thank you for the question, yeah. So I'll just stop sharing again.
Is there any other questions for the speakers?
I have one for Alessio, if it is.
Yeah, are you still here, Alessio? Might have gone for a break.
Yeah, good on.
Yeah, maybe if we take a break for 10 minutes or so before. So the next talk will be at. Okay, yeah, we got about 10 minutes.
Was mainly about
yeah, 3 o'clock in fact. Yeah, so we got 20 minutes. So yeah, feel free to carry on the discussion. I'm just going to nip and get a drink and stuff.
Sure.
And see you back here at 3 o'clock.
Yeah, see you.
Screen. Yeah, so welcome back everyone. I think people are slowly filtering back in. Our next speaker is Kaihang Shi. He's going to speak a bit about definitions of the pressure tensor in inhomogeneous fluids.
Okay. Hello everyone. My name is Kaihang Shi, and first of all, I would like to thank Professor Smith for inviting me to this conference. And I did my PhD with Professor Keith Gubbins, and I'm currently a postdoc at Northwestern University. So the topic I'm going to talk about today regarding the uniqueness of the microscopic pressure tensor is one of my PhD project. So our motivation on this local pressure tensor arises from the so-called high pressure phenomena in nano confinement. So it was recently found that some high pressure phenomena that can only occur in the bulk at tens of thousands bar can easily proceed in the nano confinements under ambient pressure. So I'm showing you 3 examples here. And first, and there's a conducting sulfur chain and high pressure crystal and high pressure hydrolysis reaction in the nano confinement. And they can easily proceed in the nano in the confinement under ambient pressure and without help of the nanopores, this phase transition and chemical reactions require larger than 1 gigapascal in the bulk. So to study this phenomena, it is intuitive to look at the pressure profile inside the nanopores, and that's why we look at the local pressure tensor. And as you know, the local pressure tensor is a second rank matrix, and it has 9 elements. For example, the pxy is the force in the y direction acting on the surface normal to the x direction. So the pressure tensor is a function of the position only, and it can be related to the stress tensor. People usually used in the non-equilibrium community. The stress tensor is also a function of the time. So pressure for the pressure tensor, we averaged out this time dependence by ensemble averaging. And I'm a chemical engineer by training, so we're interested in the equilibrium system. And in the equilibrium system, there's no stress, no shear stress, so only the diagonal elements in the pressure tensor matrix is non-zero. So in the homogeneous fluids, the pressure tensor can be reduced to a scalar pressure, so pxs and equal to pyy and pcz, and they equal to the scalar pressure. And the situation gets a little bit complicated in the inhomogeneous fluids. For example, the fluid inside a sleeve-shaped pore. So because of the forces are different in different directions, here in a sleeve-shaped pore, we have the force in the tangential pressure in the tangential direction. So tangential direction is the parallel to the surface, and the pxs and pyy they are equal, and they equal to this. We call this tangential pressure. And for the force acting normal to the surface, and it is the leading to the normal pressure. So in the rest of my talk, I will focus on the simplified sleeve-shaped pore geometry, where we only have basically 2 components, the tangential pressure component and the normal pressure component. There are 2 ways to calculate the pressure tensor. So the first method is, the first way is we call the mechanical route, and it is derived from the hydrodynamics. You can start, you can derive this by starting from the linear momentum density. I will not show you the full derivation here, but instead I'll show you here the configurational stress tensor for pairwise interactions. So you can see, so the partial derivative of the pairwise energy with respect to the vector distance between the particle I and j is the force vector, and this configurational stress tensor is related is associated with this the partial contour integral. So this is integration over a arbitrary contour connecting the molecular pairs. So this is where the non-uniqueness comes from. And in history, there are 2 popular definitions people usually use. The first one is the Irving-Cuckoo definition, which is a straight line connecting to the connecting between the particle, and the other one is the Hilashi-Mal contour. This contour is composed of 2 sections. First, you goes from horizontally from I to the j, and then vertically to the position of the j. So this non-uniqueness problem in the mechanical roots reflects the physics that there's no unique way to assign a pair force between the molecule to a particular point in the space. And this non-uniqueness problem is not particular to this mechanical root, but we also we can observe this problem or issue from a thermodynamic point of view. So if we look at a Helmholtz free energy, this is a partial derivative of, this is a differential of the Helmholtz free energy. And the pressure is written as the negative of the partial derivative of the A with respect to the volume of the system. And this is the thermodynamic definition of the pressure. And if we substitute the equation for the Helmholtz free energy into above equation, and after cleaning some mass, we have this equations right here. So the first term on the right-hand side, rho kt, this is the kinetic contribution to the pressure. And the second term is the configurational contribution arising from the intermolecular forces. So this equation I'm writing here is the bulk version, and we can easily extend it to the local version. And you can see I'm writing down two equations here. One is the local version for the tangential pressure in the x direction. The second equation is the local normal pressure. And you can see the form of the local version is similar to the bulk version. But there are two major differences. The first difference is we replace the system density with the local density, because we are looking at a slit-shaped pore system, so the density only depends on the z distance to the wall. And the second term, the second difference is we replace the system configuration energy with the local configurational energy. So right now, the configuration energy depends on the distance z. Okay, so the non-uniqueness actually comes from this configurational energy, because there's no unique way to assign configuration energy in space. For example, we can assign the configuration energy to the position of these two particles, and this is definition 1. And this definition resembles the Hiroshima definition I just showed you for the mechanical root. And in addition to this definition, we can also linearly assign this pairwise configuration energy in the space between these two particles. And this definition 2 is similar to the Irving-Cuckoo definition. And actually, you can show that you can derive the mechanical pressure tensor equation starting from this thermodynamic equation. So this non-uniqueness problem is a long-lasting issue in the community, starting from the 1950 of the Irving and Cuckoo seminal paper. They have realized this the non-uniqueness in the local stress already, but they just briefly mentioned in a footnote in their paper. So people usually ignore this footnote in the paper. And after this 1950, there's not much research on this problem until the 1980s, when John Rawlinson and Ben Whittam discussed this ambiguities of the pressure tensor in their famous book. And around the same time, Schofield and Henderson re-derived the equation for the local stress tensor, and they clearly showed the ambiguity involved in the definition. And after that, people have started figuring out the way to solve this non-uniqueness problem by imposing additional constraints to the equations. So by imposing additional constraints, we can, the people are in order, with intention to limit the selection of the contour. But until now, I don't think there's a consensus has reached in the field. And we have and of course, we are looking at the local pressure tensor. We will encounter the same issue. And we started trying to look, solving this issue from a different perspective. So different from, instead of imposing additional constraints, we look at this problem from the thermodynamic perspective. So again, I'm showing you here the differential of Helmholtz free energy. And you can see the pressure is conjugate to a volume. So, you know, in the thermodynamics, you need enough statistics to make the quantity meaningful. So if you only derive the pressure equation at a point, there's no such volume associated with a point. So our idea is it possible to define a coarse-grained pressure tensor over some space, and this coarse-grained pressure will be unique? And so here I'm showing you the argon absorbed in a sleeve-shaped pore. And this delta Z1 is the distance we defined, which is commensurate to the thickness of the adsorbed layer. So our hypothesis is that this delta Z is the smallest length scale that will lead to a unique and meaningful coarse grain pressure. So I think in the non-equilibrium community, people also call this coarse grain pressure tensor as the volume averaged pressure tensor. So to prove this hypothesis, we have to examine a lot of contours. The results, what I'm showing you here, is the local tangential pressure of the argon absorbed in a carbon sleeve-shaped pore. So on the top panel, this is local tangential pressure. And in the bottom panel, this is we calculate the integration of the local pressure, local tangential pressure. And we calculate this pressure tensor using 4 definitions, 4 different contour definitions, including 2 famous ones, Irving Cookwood and Halashima. And we also invented 2 variations based on that. And on the top panel, you can see different contour definitions lead to different local pressure tensor, local tangential pressure. And this reflects the non-uniqueness of the local value. But interestingly, if we integrate the local tangential pressure over some distance, you can see all of these contours, they tend to converge at some point. So I mark the convergence point here by A, B, and C. And if we define the distance between these convergence points, here I'm showing you the delta Z1. This is the distance that commensurate to the thickness of the first adsorbed layer. And no matter what contour definition you're using, the pressure tensor defined over this distance is always unique. It has by saying unique, I mean that it has a unique value. But here, what I'm only showing you 4 definitions. But in principle, there are infinite number of contours you can develop. So to solve this problem, we have developed a new method to explore the entire contour space. To start with, we can what I'm showing we can take the integration of the local tangential pressure from the bottom from the lower bound of the system, which is the Z wall here. And by taking the integration, we can see there are 3 cases with respect to this IJ pair. So for the case A and case C, the contour, actually the final value of the integration value doesn't depend on the contour. And only the case B, when the Z plane is intersect with the contour, the dependence of contour will take effect in the final equation. And we can take the integration for all the pairs, IJ pair, belonging to this case B. So here I'm taking the integration of the tangential pressure in the x direction, Pxx, for all the IJ pair in the case B. And the interesting components in this integration is this function Fc. So this function Fc is a contour-dependent function, and it actually embeds the contour definition in a 2D space. So if you look at the equation for the function Fc, it involves the x components of the vector in and vector im. So points n and m, they are intersection points of the plane z plane with the contour between the I and j. And if you use a different contour definition, the position of n and m will change, and of course the value of the function Fc will change. And Fc is actually a composite function. It is a function of lambda ij. So lambda ij is the relative distance of the z plane with respect to the z position of the particle I. So given a particle pair I and j, and given a value of z, we can calculate this lambda ij. So, and the value of lambda ij always ranges from 0 to 1. And if we know the functional form for this function fc, we can plug in this lambda ij value and get the results of the fc. And we can plug back the fc value to this the first equation showing you here, and we can get eventually get the coarse-grain pressure tensor. And the local pressure is just the local partial derivative is just the local derivative of the integration. And by examining this contour, the symmetry of the contour, we found that the function fc is actually a well-behaved function. And this f function fc must satisfy the following three conditions. First, the function must pass through the endpoint to endpoints. And because the symmetry of the contour, the function must pass through the middle points. And the function must be symmetric about the middle point. So based on these three conditions, we can freely construct the functional form of the function fc. So I'm showing you here, we constructed 10 types of the functional form, including those famous contour definition from such as the Irving-Coco definition and the Harashima definition. And we can see this Irving-Coco and Harashima definition also follows the three conditions we listed here. One thing you have to remember is that this function form of fc is the embedding of the contour in the 2D space. If we map this 2D definition back to the 3D, there are actually infinite number of contour can be mapped to. So although I'm only showing you 10 functional forms here, we are actually essentially examining infinite number of contour in 3D space. Okay, now we have this missing information fc. We can calculate the integration of the tangential pressure numerically. So what I'm showing you here is on the top panel is the density profile of argon absorbed in a structureless carbon silicate pore. And at the bottom panel, I'm showing you the integration of the tangential pressure. And you can see all the contour definition in 2D space, they tend to converge to some point. And this is in agreement with the results what I'm showing you before with only 4 contour definitions. And this is a much stronger evidence showing that our hypothesis is actually is correct. And we can define the distance between the convergence points, and that's the delta Z1 for the first layer and delta Z2 for the second layer. And you can see this distance is commensurate to the thickness of the adsorbed layer. Okay, so to conclude the research in this talk, I'm showing you that the mechanical approach to the pressure or stress tensor is equivalent to the thermodynamic approach. And the thermodynamic approach also suffers from the non-uniqueness problem as the mechanical approach. And we have shown that by integrating the local tangential pressure over a small region of space, we can obtain an effective tangential pressure which appears to be unique and free from the ambiguity in the pressure definition. And to support our arguments, we have developed a novel methods to explore the entire contour space and for the first time. But of course, our work is based on many simplifications, such as we started the phenomena in a slit-shaped pore, which has a very good symmetry, and we only consider the equilibrium condition. So the extension to the non-equilibrium system requires further studies, especially when there are when the system has a moving interface or fluctuating interface. With that, I would like to thank my PhD advisors, my colleagues, and my friends for supporting me on this topic. And with without their help, it is impossible to accomplish this task. With that, I would like to thank everyone for your attention, and I would like to answer any questions. Thank you very much.
Thank you very much. Yeah, Ed, do you want to take over now and take some of the questions, maybe?
Of course, yeah. So, who wants to ask a question? Any? Okay, let me. Oh, no, we have a question. Yes, please, Jesper.
Yeah. Okay. So, thank you for an interesting presentation. I was just wondering if you know about a method of playing developed by Todd, Davis, and Evans.
Yeah.
So how does this improve what they came up with?
So as I understand, in the original method of playing paper, they only have equation for the normal pressure. They don't have the equation for the tangential pressure. And I think later on, people have developed some equations for the tangential pressure, but it still suffers from the non-uniqueness problem I mentioned. So the method playing is still looking at a local value, but the method I'm developing here is a volume average value. So we actually looking at the pressure over some volume. It's not actually a local value.
Okay, so in my understanding, the method of playing is almost exact because it's in a certain point you're looking at in a plane, and you can also apply it to the shear pressure, not only the normal pressure. I agree that the original paper I think is for the normal pressure, but you can also do it for shearing system.
Yeah, you can do shear. Yes.
And I mean, it doesn't have this ambiguity with finding a function that, I mean, this contour function. And also, as far as I'm aware, if you do sort of a volume average and decrease the volume, you should be able to see that it actually converges to the method of playing. But maybe I'm just not informed enough. But you say there is an ambiguity in the method of planes. Maybe you could elaborate on this.
Yeah, actually, I haven't studied the method of plane very well. I just know the general idea. Maybe Ed, you have comments on that?
Yeah. So I mean, my understanding would be that the thing that's non-unique in the original Schofield and Henderson paper is the interaction contour. So even if you put your plane, uniquely defined at a location, whether the interaction contour crosses it depends on which interaction contour you choose. So that's where the non-uniqueness comes from, and it still exists in the method of planes form. Just because you could choose an interaction potential that may cross one plane but not another, or at least cross it in a different location and give a different answer. So I think that was the kind of original spirit of the Schofield and Henderson, the kind of objection to uniqueness.
Yeah. Okay, thanks.
I wonder if I can make a comment. Okay. I think the method of planes doesn't give you the complete tensor. You have to have one component of the PXZ or PZZ is constant, but it doesn't give you the PXX. In my understanding, that's why this work is quite interesting to me, because that's what you're looking at, the PXX. It's not constant throughout the interface. For example.
Thanks for the comment. Yep.
Do we have questions? So, I mean, I had just a question on your thermodynamic route being non-unique, because I think that's probably a controversial statement for people who have always kind of held that up as a better way to calculate the stress tensor. So my understanding is you basically rewrite the derivative with respect to volume in terms of the normal components. So the derivative in the kind of Ly direction. Yeah, thank you. The step I couldn't follow is the next one. So how did you then go from that to the 1 or 2? Is that just an integral of that expression?
So 1 or 2 is just a different definition to assign the energy in the space.
But they are things that satisfy those equations. Is that right? So they're 2 possible solutions that would give you the right form?
Yeah. So difference, if you use the different assignments, they will give you different equations. So actually, you can show that if you use the definition 1, it leads to the mechanical roots equation by the Hirashima definition. If you use the definition 2, that will lead to the Irving-Cook definition.
So, but then your argument that the non-uniqueness in the thermodynamic expression there is because it's only specified up to a derivative. So you still have this problem of having to specify some.
Yeah, if you write this derivative in explicit form, you encounter a problem how to assign the energy in the space. So what I mean is the non-uniqueness in the thermodynamic root is there's no unique way to assign a energy value in the space. You can.
Yeah, so I think that comes back to Jesper's question about that. So it is again the path. And then one other question I had is you did a load of different potentials, but one thing I noticed they're all kind of monotonically increasing in X. So you didn't have something where it kind of went back on itself. Would that still work if you had a potential that did something strange and went off and then came back and kind of doubled over?
Which slide you refer to?
I think it was second from the last, possibly. So when you went through this one here, so yeah, with all the different potentials, I noticed they're always, I think it's monotonic. Is about so you don't have one where it kind of goes off left and then comes back on itself. So it has more than one F value for a given lambda. I mean, would it still work in that case?
Yeah, I think so. Yeah. I haven't showed the full every possibility for the functional form of the F, but from some other preliminary results, I can confirm that, yes.
Okay, and then just the other point about its kind of validity, I noticed you're obviously doing it for a nanopore, which is very well structured, so you get those clear gaps between the layers. Yeah. I'm guessing for a less dense fluid, those points where it's kind of converges may not exist. So in a homogeneous fluid, for example, or one that's low density, you may not be able to find points where it kind of becomes uniquely defined.
Yeah, that's actually one issue we are thinking about. So yeah, I actually I don't know the answer. We have to look at those specific systems.
Well, it'd be very interesting to see. I think it's it's a really good sort of tool to be able to get that for these systems, and especially near the wall, where actually that's where all of the no slip and all of that non-uniqueness becomes a problem.
Yeah.
So it's possible you would use this kind of locally just in wall regions.
Yeah.
Sorry.
Oh yeah, actually, I've studied another system. It's a water inside a carbon nanotube. So we also found this convergence in that system. So you have this water layer near the surface, and we can define this delta Z, this unique length scale over one water layer in the carbon nanotube.
Okay. Interesting.
Yeah, but I didn't publish that results. I put it in my on my thesis.
I'm aware of time now, so I think we probably move on unless there's any other burning questions. We'll move on to our next speaker.
Okay, thank you, everyone.
Thank you very much. Yes. Jagjeevan Bhamra, sorry, on interfacial control friction in diamond rock contacts.
1 second, let me try and share my screen.
Perfect.
Can everyone see this?
Yeah, perfect, brilliant.
Is that visible to everyone?
Yeah, that's good.
Can you see my laser pointer as well? Is that kind of clear?
Yes, it is as well. Perfect.
Okay, that's fine. So hello everyone. My name is Jagjeevan Bhamra. I'm a second going to third year PhD student at Imperial College London. I do a lot of work with James and Daniele, who I think spoke earlier, just running through what's going on. So, oh, I'm going to skip the slide. So just quickly run through my aims for this study, really. So the purpose statement is just to understand how polycrystalline diamond composites, so PDC drill bits, interact with rock surfaces. Rocks generally have very heterogeneous surface chemistry, but alpha quartz and calcite are broadly representative of both granite and limestone. So in this study, we use alpha quartz and calcite to represent granite and limestone. For the study, we use NEMD and ReactFF. I'm pretty sure everyone knows what NEMD is, but I'll go through what ReactFF is. And yeah, all simulations done using lamps and visualization done using a VO. So just quickly running through just how the simulation is set up. Essentially, apply just a normal force on top and sliding velocity. So this is our diamond tip, and this is a calcite surface. There's water molecules in between. And we have a fixed layer, a thermostat, a bunch of layers here, and the rest is just free, really. Measure the steady state response and just collect data, basically. And I'll go through the data in the next slides. Just quickly running through what ReactFF is, because not everyone's familiar with it. So it's actually developed in 2001 by Adrian Van Duyn, mainly because density functional theory, so DFT, was so impractical for large systems. With DFT, there's large computational cost, and you cannot really use it to study like dynamic evolution of a system like you want to do in NEMD simulations. ReactFF is like an empirical method where like DFT calculations are used to train parameter sets, which can then be used to model chemical behavior. We can actually examine bonds breaking and forming, which is unlike traditional force fields where bonds can only twist and stretch and vibrate, but are never actually broken or formed. This figure here on the bottom and on the right actually shows development of ReactFF and how widely available it has become. It was actually only originally developed for carbon, hydrogen, and oxygen, but there's now huge availability. Yeah, and on the figure on the right here, we can see that ReactFF is actually broken down into 3 main branches: a combustion branch, an independent branch, and an aqueous branch. Oh, I don't know why it's doing that. And yeah, so you can see the large, wide availability, but these branches can't be combined with each other. So it's just picking and choosing the best force field that works for your system and hoping for the best, really. ReactFF is continually being updated and developed. So yeah, it's up and coming, and it's pretty handy tool. So I'm going to quickly run through what mechanochemistry is as well, because that's quite important to what we're doing. So mechanochemistry is essentially just when a mechanical force lowers the reaction energy of a system, of a reaction really, and pushes the system through a different reaction pathway. Here we can see 2 different reaction pathways. The dotted lines where mechanical force has been applied to the system, and it goes to a lower transition energy state. Mechanical stress is essentially acting like a catalyst for these types of reactions, and which may not occur under normal circumstances. Frictional heat can also induce these thermal reactions, which can then lead to solid surface wearing away or fracturing. High energy particles can be released, like electrons and photons, which are known as triboplasms or triboemissions. And these triboemissions or triboplasms can lead to electrochemical or photochemical reactions, and which can also catalyze reactions. So mechanochemistry isn't just physical wear, but it can cause other processes which can accelerate reactions or cause reactions. So it's basically just lowering the reaction barrier. I'm pretty short on time, so I'm going to try and run through this slide as quickly as I can, but essentially showing the same thing. So we can see an unstretched bond and a stretched bond. We see the potential energy of a stretched bond is much lower than an unstretched bond. And essentially, this is just another model showing how the reaction energy, or how the potential energy changes when the mechanical force has been applied. These papers down below are pretty good. They're pretty handy at explaining everything what's going on. So now the ReactFF models that we used. So on the left, we can see a comparison of DFT and ReactFF bond associations of 2 hydrogen molecules from the very first ReactFF paper, in 2001. On the right is an energy relation for oxygen bond angles, and we can see the good comparison with DFT and ReactFF. This was from the very first paper, 2000, whenever ReactFF was developed in 2001. Here we can see just the silicon and silicon oxygen ReactFF model. So these are individual parameter sets. I mean, again, you can see how DFT and ReactFF have very good agreements, which is pretty handy. Running through it. So then in 2012, David Newsom actually combined these two models we just saw. So this model and this model to come up with this model to describe silicon carbide materials. So you combine silicon carbon, silicon oxygen, silicon hydrogen, and parameterize the data set using the original data set. So we had a bunch of different organic molecules as well as silicon carbide crystals, which can be modeled using this force field. And again, we can just see the figures here compare the ReactFF results from silicon carbide equation state and for an oxygen atom binding at different positions on the silicon carbide crystal itself. And we can see that it's this very good agreement. Yeah, and because QM training sets used to develop this model, it can also represent silicon oxides, diamond, and graphite. And so it's a good model, and that's why we chose it for the study. So this described the whole quartz section of our study. Moving on, so this is the calcite ReactFF model. So for calcite itself, there's actually no solid ReactFF model published. This model is actually in development currently with Jagjeevan doing. So here on the left, we can see the accuracy of a calcium oxygen carbon angle and the calcium carbon cutoff diagonals and the energy difference between the two molecules, and how, again, like the user model, we saw that there's very good accuracy between DFT and ReactFF. Again, just more data emphasizing my point that the model that we're choosing has very good validity, and yeah, so it's just a good model to use in general. So experimental results. So this is the bulk of the study, really. So initially, we've done some tribometer experiments where we just looked at tribometer on, so diamond PDC tribometer on different rock samples, and we can see that for limestone, the friction coefficient is significantly higher than for granite. This was done in a humid environment, so not under ultra high vacuum, but so just under normal atmospheric conditions. And there was also another study done where we looked at with an aqueous environment. And the trend is still the same. Limestone had a higher friction coefficient, but it's just, the trend was more exaggerated. Also to note, it was also noted that during the experiments that limestone actually adhered to the PVC tip, so which has also been previously known. So the actual fragments of calcium carbonate is actually sticking to the diamond tip itself. So then we just did our simulations like I showed you previously. So we set up the whole simulation, and with no water molecules, we saw the opposite trend actually. We saw that, so for essentially limestone, calcite, the friction coefficient was lower, and for quartz, it was just ridiculously high. So look at 0.9. This was strange. We didn't expect this, but then we realized because we're modeling in zero hydrogen, zero water molecules, essentially it's an environment which we don't come across generally. Like it's an environment that's not atmospheric conditions, basically. It's just ultra high vacuum. So we then moved on and chucked in a bunch of water molecules. So we looked at 50 and 150 water molecules. Sorry, I don't know why my thing keeps doing itself. But yeah, we looked at 50 and 150 water molecules, and we saw the trend like we saw in the experimental results. So we saw that calcite, so limestone, has a higher friction coefficient than for quartz in both the cases, and the trend's more exaggerated as more water molecules added. There is a cutoff after 150. Not much else is happening, so the trend's still the same. So we just looked at some tip indentation stuff over sliding time, and we monitored the ploughing contribution to friction. So during the sliding phase of simulation, the tips actually indent and plough through the substrates. In all cases, the indentation depth is deeper for calcite than for quartz. This is expected because the calcite is a softer material than for quartz. Here on the right, we can just see, so for 35 nanonewton load, so quite a high load, which is about just high 2